So in this video we're going to talk about viscosity, intermolecular forces, and it's really a conflicting video for me to make because viscosity is one of those things that I could gloss over a ton of details and tell you things that are just straight up wrong and you would still get the right answer. But I also don't want this video to be overly complicated, so let's see if we can strike a compromise. So the first half of this video is going to be the watered down, kind of all you need to know for the test, and the second half of this video is going to be more factual and a bit more accurate about what's going on. So you know what viscosity is. At least you understand what the big picture of viscosity is. If I ask you what's more viscous, honey or water, you know the answer. Honey's more viscous, and you know it's more viscous because it flows slower. So the word here we're looking for is flow, specifically the resistance to flow, which is what viscosity is. Now, viscosity is going to basically describe if we apply a force to a liquid, how well does it move as we apply this force? So if we take a sheet of liquid across the surface and we apply our force, what we can do is we can take this liquid and we can break it into a whole bunch of different layers. And each layer is composed of a sheet of atoms. Now, these sheets of atoms are stuck together, just as these molecules are stuck together. Now, the force is in the direction of the flow. So we are trying to flow left to right. We're applying a force from the left to the right. So we're not really going to break any bonds between these molecules because they bunch up. Basically, we're using this atom to push out this atom, this atom, this atom, this atom, this atom. So these never break their connections. But as we look across the flow, in order for this atom to move to the right, it has to break its connection to the one directly behind it. And the same thing's true for this atom. In order for it to flow to the right, it has to break the connection between it and the atom behind it. And so the strength of these bonds is going to dictate how much force it takes to move these sheets along. So as you'd expect, as you increase intermolecular forces, you start increasing viscosity. Now, to the technical part of this video. Viscosity represents what's called shear stress. So shear stress is a force or resistance that is perpendicular to the flow. So our force is this way, our shear stress is actually in the up-down direction. So what we can write is that the force equals the viscosity relative to the normal force. So what we are saying with this formula is that viscosity is basically the resistance to normal flow. Now, this is only going to work for Newtonian fluids. And what a Newtonian fluid is one where we have this proportionality constant which represents our viscosity. Now, are there things that are non-Newtonian? Yes, cornstarch and water. If you push cornstarch and water harder and harder, eventually it will begin to flow. So suddenly you break all the bonds at once, and it's no longer this linear response. There are some fluids that as you apply more force, they slow down, they slow down. The reason why we can't discuss non-Newtonian fluids with this relationship is that what's going on is much more complicated. It's not just attractions between molecules, it's attractions within a molecule. As you take really long chain molecules and you start stretching them out, they start sliding across each other easier and easier. When they go slowly, they can intertwine and mix with each other, so it looks like intermolecular forces are going up. So, in general, for a Newtonian fluid, if you increase the viscosity, you are therefore increasing the resistance to flow, and we can increase the viscosity by increasing the intermolecular forces. This does not work for non-Newtonian fluids, so if you see things like honey is a non-Newtonian fluid. It's really viscous, but not for these reasons.